Okay, so here we are. It is week 2, Energy Y 102, and we just did a quick revision of the syllabus, so I just wanted to go over due dates with everybody. So I've covered the top portions, and the course should run itself here at this point. So week 1, introductions, there's no grade on that. We kind of took care of that in class. Week 2, which we are in right now, your biosketch is due, so please upload that. And then week 3, summary 1 is due, etc. By the time we get to the end of the semester, week 15 is essentially the few days or so between the end of class and finals, and then we'll just say, week 16 is finals, so you can sort of parse it out like that. So everything, is very similar to Energy 101, where you've got 5 summaries, 3 problem sets, and 6 exams. And I'll have a final, but the final I found is more just a sort of a fun challenge. It very rarely increases the overall grade because it is quite challenging, but there's a bonus final as well. So that's the course, and from here I want to go ahead and just look at that summary 1, because we started looking at it just a little bit last time, but I want to dig into it a little bit more and suggest a few directions that you can take it. So here's week 1. These notes, and I'll go through as we're making our way through. A lot of these notes aren't gonna change that much. I'll go ahead and click on it because I do have a few things from the Solomon review. We went over these last week. So forms of energy, units of energy. There's your definition of efficiency. I believe all of that is in your notes at this point. Yeah. Okay. Now here's the summary 1 paper, Solomon et al. And again, my motivation for putting the Solomon paper into NRGY 102 is because the course is cross-listed with Climate Change Studies 102. And so this is a big picture type of paper. Obviously, these researchers are investigating what the temperature of the planet might look like 50 years out, 100 years out, 200 years out, based on what they call the optical density of different gases. So what's a good way to think about that? Let's just pop out to the electromagnetic spectrum. That's a great place to start. And I'm going to look at CO2 absorbed. Now, one experiment that I've always wanted to do in our 2-week practicum would be to set up 3 or more chambers of different gases. One would just be atmospheric gas, one would be CO2, and one would be methane. Just set those 3 tanks of gas, transparent, out in the air, and just let the sun hit them and take their temperature as a function of time. The idea being that the greenhouse gases those chambers would get hotter. And then, is there a debate? Well, touch it and feel it for yourself. And that was one of the motivations. Now, I haven't seen that experiment done, but it seems like it would be fairly simple, fairly straightforward, something you could do in a high school physics course or whatever. But it was that question that actually led me to this paper, because they use the word optical density. So let's take it back out and just look at the electromagnetic spectrum. And I like to put it in a kind of a picture format. And there's a similar shot like this in your book. And this is actually a really good one. So the sun, being the temperature that it is, emits across a wide variety of wavelengths. when we look at when we do our PV, which is chapter 3, we're actually going to look at the individual energy of a specific photon. So what these curves are, it's really just the sum of all of the energy coming out of the sun. So this is more high temperature, high energy, your gamma rays, etc. Most of our visible light is sort of here in the middle, and then out here your radio waves, etc., as you sort of die off. So this is it's a sum of all of the different photons and radiation coming off. Now the Earth is sort of more out here. The Earth itself also radiates, as we know, the radiation coming to us from the sun. And this is actually a really good number to write down. So again, remind yourself of that 1,000 watts per square meter that hits the Earth from the sun. The Earth is actually radiating, and we'll see this when we get to the geothermal chapter as well. The Earth is actually radiating at an average of 60 milliwatts per square meter. So if let's just say we were floating around on the International Space Station and it's very cold and we're looking down on planet Earth, and you want to say, well, how much energy is coming from the Earth? And here's the area, sum up the energy, it turns out to be about 60 milliwatts per square meter. So the Earth is always giving up its energy to the cosmos. And that's what this curve is. At some point when humans invented radio waves, there's probably an extra blip out here, somewhere on the radio spectrum. When you see these images of Earth from space, oh gosh, where's all this light coming from? Oh, it looks like they discovered atomic energy, and there comes some gamma rays out of the Pacific. So this is the radiation. This is kind of the natural background radiation signature of the planet. So you sort of have, this is your input, and this is your output. So that's kind of the big picture on radiation. And obviously, we need this to keep the Earth warm, to support life. And I guess, to some extent, we need this to keep the Earth cool so that we don't just keep on cooking like Venus, for example. But what we need to do now is sort of dig down into these guys. So you can see here's water, here's carbon dioxide, here's methane, here's another HOO, which is not a common, and probably not very stable. Here's ozone again, and what we notice is that these are the wavelengths at which these different gases absorb energy. So again, the thing to think about, and I also want to make this point, and I'm going to write this down in a little note in Microsoft Word. There are really only 3 things that can happen with radiation. You can have absorption, it's a P instead of a B. Absorption, you can have reflection, and you can have transmission. So with an individual photon, those are the only 3 things that can happen. Either that photon is going to stick in whatever material it hits, it's going to bounce off, or it's going to go right through. So we're standing in a room with windows, the majority of the light is coming right through. It's obviously not going through the walls, it's bouncing off. So back to this, and some of this very high energy is just going to go right through the Earth, if it's high enough. If you ever listen to AM radio, it will actually bounce off of the ionosphere, so it's sitting out here somewhere. But the point of this Solomon paper, here's another pretty good image just showing the different absorption bands. So here's CO2, right, here we go, perfect, right there. This CO2 is right at that sort of the middle, if you will, of the radiation band that's naturally coming off the Earth. So the CO2 is absorbing that radiation rather than transmitting or reflecting it. That's the whole point. It's there. Okay. So back to, so with that kind of broad spectrum in mind, what Solomon has tried to do is add up all of that energy. So this guy right here is more or less the power of the sun. I don't know exactly why they use the term N, but let's just call it nature or natural. This is sort of the natural radiative power that hits the planet. And what I've tried to show here is that if we add up all of the, and so this, another thing to keep in mind, whether or not you've had calculus, doesn't really matter, but that integral sign is just a symbol for summation. It just means that I'm adding up all of that radiation. So, think back to that radiation curve. I'm adding up every single photon that hits the planet from T, and so the bottom is T initial, and the top is T final. And if I just keep adding up energy over and over again, what you kind of like to have is an energy balance, where the whole thing just kind of adds up to zero. Whatever comes in equals whatever goes out, and everything stays the same forever and ever. We know that's not true, of course. There are a lot of other factors that affect the climate. Volcanoes go off, the Earth is in a specific place in the Milky Way, some other little gravity messes with the orbit, all kinds of things can affect that. But living in the so-called Holocene, as we do, have you guys heard that word before, the Holocene? So living in the Holocene, we'd sort of like that to stay where it is. Okay, but there is this F, this sort of forcing function, and what I've shown, this is basically the radiation that is attempting to leave the planet, and this radiation could be coming, straight from the ground, from a volcano, from your car engine, from a nuclear power plant, whatever. So anything that's hot is trying to get rid of that heat off into somewhere. But if this arrow starts at the Earth and only makes it this far, the heat stays behind. Okay. So what we're looking at right now is the natural, natural heating state of the Earth is the forcing function, sort of whatever stays in the atmosphere, minus, and this is the sort of the catch-all, this lambda, times the change in temperature. So the atmosphere itself, and I haven't drawn this in here, but if you're copying this in your notes, you can sort of have this this little blanket of air as having a temperature, and that's exactly what the authors are studying. And obviously we know that the Earth's atmosphere is not the same temperature everywhere. It has a number of different temperatures, but you can add them all up and get some average. Also worth noting, this lowercase t is time, the uppercase t is temperature, and this funny looking triangle is delta. So every single one of the plots in their paper is looking at the change in temperature as a function of how much sunlight hits the Earth minus the amount that's leaving. Okay. Yes?
So you said that little symbol that kind of looks like a one that you have underlined?
Yeah.
That one's just a sum symbol?
That's a lambda. No, that's a lambda, and I'll write that out for you. So, in fact, I'll just do it this way. N equals, oops. Yeah, let me make this a little bit bigger here. Okay, so N equals F minus lambda, and I'm typing this out. In fact, it's usually better to use a serifed font. So n equals f minus lambda delta t. If I come in here and change that from Times New Roman to symbol, we get that. Okay, so it's a power equation. That's what it is. So it's a radiation power equation. And remember last week when I wrote on the board, we did force, then we did energy, and we did power. It's critical that when you write your equation out, what am I adding up? Am I adding masses? Am I adding volumes? This is a power equation.
So lambda in this case stands for?
About to tell you, it's a good question.
You're
Yeah,
about to
yeah. But the delta means a change. It means that the temperature was
Yeah,
at one
delta.
temperature at one point in time, and it's going to be another temperature at another point in time. Okay, what are the units of lambda? There we go. She's not a plant, I promise. So what I've done here is just for the sake of argument, since we know that all of the units in the units of all of the variables in the equation have to be the same, I've just sort of gotten rid of f to say that, well, let's just assume that humans don't affect the atmosphere and sort of take them out of the equation, just so we can get at the units. We know that this is power. This little symbol right here, I don't know if you can see it or not, there's a dot over the equal sign, and the dot means n is approximately on the order of, well, I left out the negative, it's not important in this case, but n is approximately negative lambda delta t. So, how do we figure out what lambda is? Don't get it by itself. Yeah.
So F is some factor that's affected by humans, not just what's re-radiating out?
You know, that's a good question. That's a good question, and I'm not sure I know. I'd have to dig back into the paper to answer that specifically. It could be any anomaly. I think it's just sort of a catch-all for any anomaly.
Okay, it's not like just what naturally is radio-reflected.
Well, I guess then that kind of gets into your definition of natural. You know, it's like, okay, well, humans are here, we're part of nature, and it's yeah. I'll dig back into the paper and answer that, but it's what's called the forcing function. It's what's leaving, and it could be, it could be completely anthropogenic. It could also be something that's not. But just based on your question, though, there's not. There's only one factor there. So what the author, I'm going to say it's the latter, was just everything. If a volcano goes off, that's going to do the involve the forcing function.
So everything that's leaving.
Yeah,
Okay.
That's the way to think about it. Yeah.
And N is everything that's coming in?
Yes.
The Earth being a closed system, it would be easier to measure the things that actually do leave the atmosphere.
Well,
Because not
what do you mean by
yeah.
closed system?
Well, in particular, the atmosphere is so thick that a lot of the gases or emissions that are floating around in spheres don't actually radiate like pure energy would from our
Yeah,
general
it's trapped.
atmosphere.
Well, I suppose, but we can't just make the assumption that the Earth is a closed system, because if the sun suddenly went off, the Earth would lose all of its energy in space.
Right.
So we have to treat the Earth as an open system that's radiating into space.
An open system part of the solar system.
Sure, part of the universe or whatever. Yeah,
Okay.
yeah. So we have to treat it as an open system. So what I've done here is to say that the forcing function is, relatively small, and the Therefore, the natural incoming energy, incoming power, is approximately equal to lambda t. And I've taken the delta out because the delta does not have any units associated with it. So in algebra, when you're trying to determine what your unknowns, you put your unknowns on the left-hand side. So I've got lambda by itself. And we know that n is measured in watts. As we know, this is a power function. We know that temperature is measured in Kelvin. And as it turns out, and I'll put another step in here because I think it's kind of a leap here. But as it turns out, watts per Kelvin ends up being the change in entropy over time. And this little s dot, let me get through this whole slide, then I'll go back. This little s dot means, so a dot over a variable means the time derivative, or it means the slope of a curve. What do I mean by that? Well, we know that the universe is always becoming more and more entropic. That's the second law. What the second law does not tell us is what the slope of that curve is. Second law just says, it's gonna go up. Sorry, but it's been going up since forever, and it's gonna keep going up forever. You might cheat it a little bit. You can cheat the second law by putting energy in, but on average, that slope is always gonna be positive. So here's time. So the slope of that curve, is lambda. Slope of that curve is lambda. So what it is, and the authors don't come out and say it, but it's the entropization rate of Earth. It's the rate at which the Earth is becoming more disordered. Now you could say, well, let's fix that. Let's make it neater. Let's I don't know, take all the nuclear waste and fire it off into space, or there's a lot of different ways people are like, let's just clean the Earth, right? But at the end of the day, the universe, the second law is always gonna get you somewhere. So that's what that is. And let me give you one more little equation here, because we know that S, entropy, or the change in S, let's do it this way, equals the change in heat over whatever temperature where we're operating. And since delta itself is not a variable, it's just a symbol, we don't italicize it. And I say that because when you write your equation in your summary 1, I want you to make sure that you do italicize all of the variables. So you can see that I've italicized n, I've italicized f, I've italicized t. I didn't italicize lambda. It looks weird enough already. So, but I just left the delta as is. So Q in particular, so S is entropy, just write that down in your notes, S is entropy. Q is thermal energy. Q is always thermal energy. And again, the symbols used in Solomon are N and F, but N and F are, it's energy, it's radiation. The sun, all of the energy we get from the sun is from radiation. It's not from conduction, it's not from convection. So that's what that is. So, and let's take one more peek. I'm going to go back in, see if I can answer the question regarding the definition of F. Let's just take a quick look at it.
Is it possible by the sun's rays reflecting off of the moon that would affect?
Sure, sure, yeah. We get, I mean, it's not much, but,
Right.
yeah. Okay. Well, so, all right, well, yeah, right there. F is the added added energy due to antiprogenic radiative forcing. And the definition they give is N is the net heat flux. And so on that note, I think let's think of it this way. I don't have my little pad going, but the in that diagram where I showed N, just coming towards the Earth, think of that N more as a two-way arrow. It's the net. The N is how much comes in minus how much comes out. So I just showed it going in, but think of N more that way. So that's the official definition. N is the net. So my initial statement that it's natural was not quite right. N is the net. And what we'd like to think of is N being 0 so that the temperature stays the same. There we go. Yeah.
So by net, they just mean like as a whole?
Right,
kind of thing?
right. So some radiation comes in. Yes, let's go back to that. So some radiation, it's basically what's coming in minus what's leaving.
Okay.
Yeah. So it's more or less this minus this, keeping in mind that we only receive a tiny fraction of all the radiation that comes off the sun.
So the incoming energy would successfully push energy that already exists in the system out?
Well, I guess in a sense, the hotter the sun makes the Earth, the faster the Earth radiates. So yeah. The hotter you make your bathtub, the faster that radiation leaves your tub. It's true. Yeah.
Sorry, so
I don't
then
know.
that's what lambda is? Lambda is the in minus the out?
Lambda is not the in minus the
No?
out. It's
Okay.
lambda is it's the slope of the entropy curve. It's a little weird, but that's what it is. Yeah, N is the in minus the out.
Oh, N is the.
N,
Oh,
yeah, the letter
okay,
N,
yeah.
yeah.
That's why I'm
So
confused.
I was writing
N.
I was writing N before as nature, but the definition is it's the net flow. It's the net flow.
So lambda, or the slope of that curve,
Yeah.
is essentially just the rate at which energy is approaching. The whole entropy thing is it's approaching a steady state, right?
Or instability?
Yeah, entropy's a hard one. for me.
Entropy is not an easy one. Entropy is not an easy one. The what's a good way to think about it? So right now, let me
Boiling water and how it starts just tipping and spitting everywhere, that could be entropy in a way.
well, let me actually,
Because that paper we read last semester, I mean,
I know, it was a challenge.
vague idea at the end of it, but
Yeah, it was a challenge. So here's a really good example of entropy. This is the Richard Feynman definition of entropy. So we've all just been in the ocean swimming, and we've got some salt water on us and some sand maybe, and we're in the bathhouse and we're gonna dry off. And there's one towel, and there's no sand or salt water on the towel. So the first person uses the towel, and now there's no more sand and salt water on the person, it's on the towel. Next person uses the towel, they get most of the sand, the salt water. The towel's got a lot more sand and salt water. Third person uses it, I'm feeling okay. By the time like the fourth or fifth person uses the towel, you might as well just not bother. because the sand and the salt water are everywhere. In another example would be, let's just say, we said we're gonna make an addition to this room. Like, oh, the room's not big enough, we need more space, so I'm gonna double the size. Right now, so out in that cold room that we just built, there'll be the same number of molecules, atoms, whatever, moving around, and they're going to be moving relatively slowly, which is a relatively low entropy state, because you kind of know where the things are, because they're moving slowly. In this warm room, give me one more sec. In this warm room, things are moving a little hotter, and there's more entropy. As soon as we open those two up, everything's just kind of the same, and you can no longer do any work with those, because everything's just kind of warm and lame.
I'm trying to equate this textbook definition here
Yeah.
on our screen to your towel definition. It says, often interpreted as a degree of disorder or randomness within a system.
Yep.
So would that be like the randomness of how much salt water and how much sand are going from the towel to the body or vice versa?
Yeah, it is, because if we say that initially we know that the towel does not have any sand or salt water, like you know that, and it's all over here on the body. As soon as you start mixing those two systems, yeah, it's everywhere. So so that by the time the fifth person uses the towel, was that chunk of sand originally on me, or was it on the towel, or where was it? So you can think of that as randomness. Yeah. It's not an easy concept. People have been struggling with it for. Yeah.
A measure of a number of specific realizations or microstates within a system.
Right.
That sounds totally different.
Well, okay, so that's. Okay, so I could.
That one makes more sense to me.
It does. Well, it does. So, and here's the way to look at it. This is sort of the macro. The micro. Well, let's do it this way. So, at the micro scale, if I have let's just start with a chunk of ice, like an ice cube, that's well ordered, or a snowflake, some kind of crystal structure. If you know where one of the molecules or atoms in the ice cube is, based on the crystal structure, you can predict where everything else is. You start to heat it, the water starts to move, it starts to melt. Now it's kind of everywhere. It can be a lot more places all of a sudden. Heat it more, now it's steam. Wow, it's everywhere. So each one of those water molecules, that H2O, which was like, I know where that is. There's very high probability. It's kind of like the start of a NASCAR race. Everyone's lined up, orderly. There they are. Once you start putting that energy, oh gosh, there goes a wheel, there goes a tire, that guy wrecked. That car's on fire. That's another way to think about it, in terms of the total number of states that all of the parts in those cars can be in, just increases once you pump that energy into it. So you can kind of think of the cars as a little micro set of
Or it
molecules.
decreases as energy is taken away.
Say again?
So it increases as energy is put in.
Yeah.
And decreases as energy is
Yeah,
taken away.
sure, yep.
So as the universe approaches a steady state, that's where the slope is always positive.
Yeah, there's some question about that too. So if we go back and look at this, there's another way to look at it. You can look at entropy in the same way that you can look at mass. So you could have two things of the same mass. You could have a pound of lead and a pound of feathers. The pound of lead is going to occupy a smaller space, but they still have the same mass. Now, you could also have two volumes that had the same entropy, even though the volumes were different. So you could have a very small disordered system, or you could also have a very large disordered system. So at some point you can divide the, and really all it is, if we go back again, it's just change in heat divided by temperature, that, and again, two different systems could have the same amount of heat. You know, I could have a boiling pot of water with a certain amount of heat, I could have a chunk of lead with a certain amount of heat. So you can compare apples and apples, with, in the case of entropy. But what's more difficult to think about is, as the universe expands, is there really more disorder per unit volume, or is the universe expanding fast enough to absorb disorder as it's forming? Yeah. So. Yeah.
So,
Yeah.
so then entropy is directly related to energy input or heat input?
It is.
It increases the entropy?
It is. Yeah.
Because the molecules move faster, so it's more disorderly?
Yeah. It is.
That makes
Yeah.
it more
Yeah.
interesting.
Yeah. It is. And you can, there's different ways to add energy to a system. So if an earthquake were to start happening right now, the chairs would become more disordered, the furniture, things might start cracking. So that's sort of a negative way to add energy. Or but if we've got our HVAC working just right, we might, we'll heat the room and everyone quits being agitated and calms down. Or if it's too hot, we cool the room to make things, more orderly too. Yeah.
The same can be considered in the physical realm of atrophy, where some of these physical states starts to deteriorate, and the accuracy of the physical actions will decrease. Like, what they're trying to do will be that much more difficult to accomplish.
Yeah, that's a good analogy. Okay, so with that in mind, I want to just take you back to what I'm expecting for summary 1. You do have to use at least one equation. You do have to use at least one equation, and you have to use at least 300 words. You have to use a Harvard citation, and you actually have to use you have to have two separate citations. So cite the Solomon paper, then find a second paper. Sometimes people go out and look at Carnot's original work.
It's not a bad idea.
Yeah. Go ahead and use single spacing. When you turn it in, use your last name, and then summary 1, summary 2, energy 102. Yeah, so that's how I will grade these. Take a look at that. So again, you need at least one equation, 2 references, 300 plus words. All right, any other questions on summary 1 before we move on? Oh, and you are required, I should also make this clear, you are required to upload your summary 1 twice, put it up for peer review, let your classmates take a crack at it, and then upload it there for me to grade.
So then we should upload them obviously before it's due to peer review.
Yeah. And if for some reason, I'm not going to go back and look at those peer reviews until the end of the semester anyway. That's kind of your place. But if I go back and, gosh, you never peer reviewed anybody's work, then that's a problem. That's a problem. Then start bugging your classmates and just email it around. Say, hey, Kat, could you have a look at this? Daniel, would you mind, spending a couple minutes on it? I did the same thing. I sent Steve Running a copy of my book, and he hasn't reviewed it yet like I asked him to, and I had to bug him last night. So just, be nice, be friendly. Yeah.
I was going to say, you should just make a part of the thing, is it when you go and input it into the peer review section, just do a review of somebody else's too.
Yeah, sure, yeah, a little give and take.
Yeah.
And if you see someone who doesn't have any reviews yet, give them a review. Yeah, you'll keep punching the poor person's got to. Yeah.
So just the due dates, and it looks like, that it includes 16 weeks, so that would include finals week, correct?
Correct.
Okay, and spring break.
Um,
That's counted 3 times.
yeah, I suppose.
So it would just be something we do in spring break?
Yeah. I think there are 16 weeks total.
I've counted like 3 times. So
Did you look?
I
Okay.
can't count.
Well, let's.
consistently.
All right.
I think that's right.
All right. Well, I'll look at it a little more
Okay.
closely. Yeah. And if we need to, yeah. Well, if we need to have something due, or like 2 things due when we come back from spring break, we'll just do that. Thanks for looking at that, though. Thanks.
So what are the guidelines for this period, or for this summary? It's just, I know that you just went over the rubric, but what is the
Oh,
topic?
yeah.
The topic has to be,
Oh, it's
I think,
a response to a research paper.
oh, that research
Yeah,
paper that
provide-
you just went over?
yeah.
Okay. How many words?
Same, 300 plus.
300?
Yeah.
And just do you want every sentence that we use to be paraphrased with citation, or?
Oh, you mean,
can it
yeah, like
just be
put in there
summarily,
the
summary?
page number of the thing, right? Just author and page number.
Oh,
Like-
just cite the paper ones.
Okay.
Okay.
And don't cite the page number.
Okay.
No,
You
no,
don't
no.
have to do it in text.
No, don't do the text. No, just cite the paper ones.
Okay.
Yeah.
What about for the other paper? Since you're citing another paper, should you do in-text citations?
No, don't worry about the in-text. I mean, you can if you want, but it's not gonna be important to me. I'll just,
Okay.
I'm not gonna go and make sure you got the right page number. Just, you went out and found something else and cited it.
Okay.
Yeah.
So as long as you include some information and then the citation at the bottom, it's okay?
Yes, exactly. Yep, exactly. So I think this answers your question, Daniel. 300 words, 3+ paragraphs. So you have to have that second paper and an equation. So. Okay, let's just take a break.